All right. So in today's lecture, we will continue talking about registers, and then we will get into counter design. Couple of announcements before we do that. Today, Tuesday, November 17th, we are working on homework 9, which is due tonight on Gradescope. The next homework 10, will be posted later today. The studio that you guys are working on, the scrolling display one, that's studio number 7. That is due after you come back from Thanksgiving break, but please do not leave it to the end. Try to get it done as soon as possible so that you don't have things bothering you during the break. And some of you already have completed working on that, so that's a very good encouraging news there. The last studio for our course, Studio 8, will be assigned in a few days. There's no hurry. It's going to be a LogicWorks based studio. It is going to be due on the last Wednesday of the semester, December 9th. Daily quiz for today, quiz number 20, is available on Gradescope for you guys to answer. 4 questions shouldn't be that big of a deal here. Okay, so the next thing that I want to do is talk about exam 2, and those are the numbers for exam 2. So 71 students, that's more than half the class, way more than half the class is above a 90 mark. The average is a 90.24. Almost everybody is above a 50. So all in all, it's generally it's been a very, very good outcome from exam 2. So that's very good to see. Now I hope that you guys can repeat this sort of performance even on your final exam. Note that final exam is scheduled by the registrar for December 16th. Let me just write it down over here. Final exam, December 16th, and it is scheduled for 3 to 6 p.m. Eastern, but we will do what we usually do. We'll open it up for the entire day. You guys can take it anytime during the day, but because we have 3 hours, I may extend that exam. Instead of it being 2.5 hours, I may make it 3 hours. So you have a bit more time for that. The final exam, however, is going to be comprehensive. So that's one thing that is going to be different. So you are going to see everything from the first lecture all the way to wherever we stop. Let's see. How about regrades? So in case you guys have any regrade requests, please email them to me in a week. Regrade requests. Email me at hameem2@rpi.edu. So we are talking about before November 23rd. November 24th. So email them to me if you guys have it. Any regrade requests, explain me the situation, and then I will take a look at it after I receive all the requests. Questions or concerns about the statistics for exam 2? Okay, let's move on. We are going to go back to our register. So Sierra asks a question. Multiple choice question 8. No partial credit for one correct selection. Yeah, unfortunately not. This was consistent for all the students. It's consistent. It's relative grading, Sierra. All right. Let's continue talking about registers here. So we are going to talk about 74X194, which is a 4-bit Bi-directional, so it can go either way. It can shift things either way, left and right, and it is going to be a universal shift register. So we can do a lot of interesting things with this chip 194, and let's take a look at what all things can we do with this first. So what I'm going to do is I'm going to highlight 4 different modes that it can operate in. So it can operate in 4 modes that are going to be essentially set by S1 and S0. S1 and S0 are 2 active high inputs on pin number 9 and pin number 10. So depending on what you set for those S1 and S0, that's going to dictate which mode your universal bidirectional shift register is going to operate in. Now, suppose you set that to 0, 0. So S1 is 0 and S0 is 0. Then you are going to be in the store state, which essentially means the outputs over here are not going to change. They are going to be in the store state, which means QA plus is, so essentially this means QA plus equals QA, QB plus equals QB, and so on. You guys get the idea. It's going to be in the store state when S1 and S0 are 0, 0, so they don't change. Next, we have 0, 1. So S1 is 0, S0 is 1. In that case, we shift right. So what does shift right mean? As you can see here, the outputs are going to essentially scoot to the right. So QA is going to move to the right, QB is going to move to the right, QC is going to move to the right. But then that opens up a blank spot over here. And that blank spot can be filled by a new bit. This is not circular shift. This is 3 bits moving to the right, which opens up an empty place on the left, which can be filled by a new bit that you enter over here. So for example, if you attached a 1 over here, 1 would go over there. If you attached a 0 for SR, then a 0 would go in over there. So you control what goes in as the shift right input by controlling pin number 2. And in the similar manner, you have another mode here, which is 1, 0. So S1 is 1, S0 is 1, 0, in which case you do a shift left. Shift left essentially means that from, let me use green, say. From this guy, you're moving shift left here, left here, left here, and then that opens up another spot which you can fill using the shift left input. So whatever you attach on pin 7, a logic 1 or a logic 0, that gets filled up in that empty slot when you do a shift left. The fourth mode here is sort of pretty straightforward. 1, 1. 1, 1 essentially is for parallel load. Parallel load means put 4 things over here. Soon after the positive edge of the clock, the 4 things will appear at the output. So essentially QA plus will be A, QB plus will be B, and so on. So you're doing 4 bits loading into the register all in parallel. There's a question in the chat box. Does this only shift once when the shift input is turned on, or does it shift? It continuously shifts depending on the clock, right? So the clock is going to control, so it is going to do a shift operation at every positive edge of the clock. So as soon as this chip sees a positive edge, it is going to go monitor the 2 mode bits. And depending on the mode bits, it is going to do one of these 4 operations. And it does that every positive edge of the clock. So the answer to that question is the clock. Yeah, it's going to run continuously as long as you keep running the clock. So we talked about the modes, we talked about SL, we talked about the 4 things that you can parallelly load, we talked about the SR input or the shift right input, and then this is sort of obvious, the positive edge of the clock, and we also have an active low asynchronous clear. We all know what that means. Asynchronous clear means that it is not going to wait for the positive edge of the clock. It is going to clear the register as soon as pin number 1 goes low because it's an active low input. So I hope that that is clear. Now let us try to learn more about what is inside this chip right here. So let's take a look at this. Now, when you look at this circuit diagram, logic diagram, it might seem very overwhelming just because the number of gates are many. But if you try to break it down, it is actually quite simple because you can see 4:1 muxes in here. And I'll show you where it is, right? So if I zoom in over here and I focus on, for example, just this piece, let me do it for C. Right here, right here, right here, and right here. Oh my gosh. Better. So if you look at that, that is essentially a 4:1 mux that I'm sketching over here. Now, what I'm going to do is I'm going to attempt filling out all the details over here depending on how the things are connected over here, right? So let's go one by one. First of all, what are going to be my select inputs, right? The select inputs for the 4:1 mux, what are they going to be? So for that, I'm going to need to go in and take a look at where are my select inputs. You see, the select inputs S1 and S0 are actually going into each one of the 4 AND gates. So if I look at this AND gate, I'm going to use a marker here to mark this out a little bit. Oh, sure. And then if I track it down, you see, so that is S1, and the next guy is going to be S0 complement. So you see, if I put it over here, this was S1, too big. This was S1, this was S0 complement, telling me that if you set the mode to be 1-0, this guy is going to get through, right? Whatever that is. And what is that? Let's backtrack. See that? So QD is actually coming in, right? From here to this. So what is happening here? QC over here, the output of the second D flip-flop is actually going to be the output of the first D flip-flop. If I use that, you guys see that? That's when it is 1-0. So for 1-0, I'm simply going to say left, right? Because you see, things are moving down, right? Things moving down indicate a left operation. There are a couple of questions in the chat box. What is the parallel load again? So parallel load is essentially if you wanted 4 bits. So suppose you wanted your register to hold 1010, right? If you wanted your register to hold 1010, you would simply provide 1010 at the input, and then you would use the positive edge of the clock to load those 4 bits into the register. So this becomes 1010 after the positive edge of the clock. All right, so I hope that answers that. Let's go back. So we talked about left, right? So let's fill it up. Now to fill it up, this guy up, my most significant select is S1, my least significant select is S0, and I have looked at the case where it was 1 0. So for 1 0, I know that it is going to be a left shift, and this is essentially going into the D input, right? Because those are all feeding into the D inputs of the 4D flip-flops, so that after the positive edge of the clock, they can appear at the outputs of those D flip-flops. Let me erase those quickly. And let's go do the others. So let's say what happens when it is 0 0, right? So if S1 and S0 are 0 0, what is getting through? Well, whatever that is getting through, right? So let's track what that is. It is the output of the D flip-flop. So output of the D flip-flop is being fed back into itself. So that's essentially going to account for a store operation or a hold operation. So that happens when it is 0 0. So let's do that. This is going to be current data, whatever that is, right? QC plus will be equal to QC. Next, 1 1. So when it is 1 1, S1 is 1, S0 is 1, and what goes through? The new data will go through, right? So the new data essentially indicates that we are essentially going to use this for parallel load. So this is going to be new data for the last input. And then we are left with 0 1. So this is going to be for 0 1. And what is going in? This guy. Where is that coming from? I would have to track here. This guy is coming from QB. So QB is essentially moving up to QC, which is a right shift operation. So you see 4 things depending on S1 and S0. Current data will go through. That means you're in hold state, or you can do a right shift, or you can do a left shift, or you can do a new data that's going to account for parallel load. That is going to go into the D input, the D flip-flop input, so that after the positive edge of the clock, your outputs, Q pluses, can change according to D plus, right? Because Q plus equals D. So whatever you provide at the input after the active clock edge, it will appear at the output. All right, questions about how this guy is going to work. Essentially 4:1 muxes broken down.
Could you trace back the third input of the 1 0 again?
1 0, right?
Yeah.
Okay, so here you see that's at the top, right?
Yeah, that one.
Are you okay with the S1 and S0 selection?
Yeah, that makes sense. Yeah.
Okay, so now if I look at the third input, right, this guy right here, I would have to track back. Okay, going further up. All right, from here. Right there. Right?
Okay, I see.
So QB
and so
is essentially moving down to QC, right?
yeah, I see that now. So also you said the S1 is S1 and the S0 is S0 complement?
Just for this guy.
Okay.
Because 1 0.
Oh, right.
So,
okay. Got it. Yeah. Because they would both need to be 1.
Right.
Right.
So if they're both 1, then this AND gate is active, right? So the 2 bits inside these AND gates are essentially suggesting what S1 and S0 need to be for their corresponding third input to go through.
Right. Yeah, it makes sense now. Thank you.
No problem. All right. Good questions, guys. Keep them coming. Now, you might see that at the end, very end, you have the shift right input that only corresponds to this one last D flip-flop for QA, right? Because that's the only one I need to worry about, because those are going to be at the edges, right, with the empty spots that get created. And similarly, the left input is going to be for QD. Everything else will be a shift between itself, just as we did over here. The empty spot here, the empty spot here. All right. Talked about 194. Now, this is also like a zoomed in version of one of the 4:1 muxes. We have talked about this earlier as well. So let's finish filling this up. This was S0 and S1. This was going into this guy right here, right? Let me use red. And this was QC, because QC plus is QC here, and then this was QB, this was QD, and this was our new C, right? Let me highlight them or color code them. This was QC because and then I cannot see QB and QD because they are left and right shift coming from top and bottom. So essentially zoomed in version of whatever we just saw. All right. For in terms of applications, we can use a UART transmitter receiver, right? So for transmit, so this is one of the applications of your universal shift register. For transmit, you would read a word parallelly into a computer, then write it bit by bit to a serial data communications line. And for that, you would need to use a register to hold those bits temporarily. And as you are receiving them, you can read a word bit by bit from a serial line into a register, hold it for temporarily, and then the computer can read that word in a parallel form all at once from that register. So essentially, using the register as something that holds the bits that you're trying to read and write with respect to a computer on a communications line. Now, let's try to get into the concept of counter design. But for this example here, we are going to use the Universal Bi-directional shift register, the 194 chip, to design a counter. And this one is a standard configuration, and it's called the ring counter. And the ring counter is essentially due to that wire there, the feedback wire. My goal here is to essentially determine the operation of this circuit. So we'll start with understanding how it is wired up as. So you have the 74194, right? Universal bidirectional shift register, the one that we just looked at. You have the positive edge of the clock controlled by the clock input. You have the active low clear connected to high, which means that this guy is never getting cleared. S1 and S0 are connected to 1, right? This guy is connected to 1 already, hardwired, right? This guy is hardwired to 1, and this is actually controlled by this reset input. So I'm controlling S0 here. My left input is coming from QA, and I have hardwired the inputs DCBA as 1, 0, 0, 0. And I'm not using the shift right input in this case, because I'm using this as only a shift left register, because of S1 being a 1 and S0 being either a 0 or a 1. When it is a 1, we do a parallel load. When it is a 0, we are doing shift left. So let's see, what are we going to do here? It is already wired as a shift left register, because S1 is 1 and S0 is 0, right? However, when S0 is 1, we know that we are doing a parallel load there, right? So let's start with this. Let's start with, if I go over here, let's start with the clock is going as is, right? Clock is a free running clock, a square wave, that's fine. But let us start with our reset input being a 1 for some duration of time, the initial duration of time. So when it is 1, if I go back here, when it is 1, we know that this is going to do a parallel load. What will it load? If I need some space here. It will load the A, B, C, and D into QA, QB, QC, QD. And A, B, C, and D are already hardwired to 0001. What does that mean? After the positive edge of the clock, this will be 0, this will be 0, this will be 0, and this will be 1. We have loaded things parallelly into the universal bidirectional shift register using reset as 1. But we do that only for the initial few moments. Soon after we have loaded things into the register, the parallel load, we are going to transition this to a 0. We are going to make that a 0, indicated over here. And as soon as we make that reset 0, we have this guy as S1 is 1 and S0 is 0, which means we are doing a shift left. So let's try to see what happens in the shift left operation. We are going to have to wait for the next positive edge of the clock, right? As soon as the next positive edge of the clock happens, tell me what is going to appear at the 4 outputs in that order. Q0, Q1, Q2, Q3. What will you see over there? 0, 1, 0, 0. That's perfect. You see that 0 is fed back into the left input, which is going to appear over here. This one will go down. This 0 will go down. This 0 will go down. So what you will have here is 0, 1, 0, 0. Perfect. What will you have after another positive edge of the clock? After the second positive edge, isn't Q0 least significant? So in this case, there is no least significant, most significant. Because it's all registers, right? So the significance is up to the user, however they want to use it. So if you want to Q0, you're right. So Q0, the fact that the subscript is 0, you can treat that as least significant, right? So you can read it as 0, 0, 0, 1, 0. That's fine. It still wouldn't affect the movement of the bits though. All right. So after the next positive edge, 0, 0, 1, 0. Let's see. 0 goes in, comes here, that 0 comes here, that 1 comes here, that 0 goes there, right? Perfect. So you got another 4 bits. All right. What happens after the next positive edge? So shift to left means data is moving from QD towards QA. Yes. Right? Left was moving down, right? Left is moving down. So that what is moving down? QD will go to QC, QC will go to QB, QB will go to QA. Oh, no. It's still not circular shift. It is looking like a circular shift just because of this connection right here. So it's external, right? The connection was made external to the shift register. All right, let's, so you see, Ian, the circular shift nature is not inbuilt in the chip. You would have to do that outside of the chip to do a circular shift. Would the next iteration be back to this? All right, let's see. The next iteration will be actually 0, 0, 0, 1, right? And then after that, you go back because 1 now goes back into it to come out here. That, and notice that our initial state is back now, which essentially means this is going to keep going on like that, right? 1, 0, 0, 0. But for this example, is this a circular shift register? Yes. The way we have connected it, yes, because Q3 goes into left input. You're right. Now, there are a few problems with this counter. One of the problems is how many values is it counting? What is the counting sequence? Of this counter. So it starts with 0, 0, 0, 1. So it starts with a 1, right? In decimal. What does it count after that? 2, 4, 8. Perfect. What else? After that, it's back to 1. So it is counting 1, 2, 4, 8, 1, 2, 4, 8, 1, 2, 4, 8, and so on. It is a 4-bit counter, right? A 4-bit counter, you would ideally want that to have 16 possibilities, right? Ideally, you would want that to be 0, 0, 0, 0 all the way to 1, 1, 1, 1. Because that will give you the entire counting sequence. But instead, over here, we only have 4 out of those 16 possibilities. So it's limiting in terms of the number of states the outputs will have, the counting sequence will have. But that's not the big problem here. Why isn't it 8421? Oh, just because we are treating Q0 as least significant. There's a bigger problem than that. Anybody? Anybody wants to guess what happened? Use a 422 encoder if you wanted proper decimal output. Sure, yeah, you can do that. Absolutely. Yes. That would be brilliant. 422 encoder, yes. You would not do 422 encoder because this is already encoded, right? Decoder, yeah. Now, guys, look at this. What if you lose any bit that was 1? What happens then? So, question is, what if the 1 gets corrupted? You got it. You are going to go into a 0, 0, 0 cycle and you are never going to come out of it, right? Because only zeros will be the entire, yeah. Well, I wouldn't say the entire system breaks. I would just say that you will go into this infinite loop of cycling zeros back into a register, right? So that's not a useful counter at all. You are right. If you use reset, you can bring it back in, but unless you do that, it is going to keep counting zeros. So that's a problem with the ring counter, that if any 1 get corrupted, the 1 in the cycle gets corrupted, then we only keep cycling zeros. You could put an OR gate on the outputs into a reset. Sure, yes, you're right. They could, but there would be a need for other hardware to be incorporated with this design to do that. But what if I don't want to do it? What if I don't want that additional input? There is another counter which is a little bit better than ring counter, which we'll talk about in just a bit. Let us finish talking about this timing diagram here. We talked about the reset input. First, it was doing a parallel load. Then it was doing a shift left operation. And while it was doing that, our outputs, Q0, Q1, Q2, Q3, they were doing these bits, right? So for example, we did 1, 0, 0, 0, and then 0, 1, 0, 0, then we did 0, 0, 1, 0, and then 0, 0, 0, 1, and that one came back in, and then we did the cycle back through, right? So if you look at these 4, and then we did this, and back to that, right? So it was counting 1, 2. The states were S1, S2, S3, S4, but it was counting 1, 2, 4, 8, and then back to 1. So that was the counting sequence. Now the other register that I mentioned is the Johnson counter. And the benefit with that is that corruption of bit 1 will not be a big problem. There is a way to automatically recover from it because of this NOT gate here. We'll talk about that in just a minute. And it also goes through more than 4 states that the ring counter was allowing us to do. So what are we doing here? Again, we do the similar things. Clock is controlled by a positive a clock input connected to the positive edge of the clock. Our reset underscore L input is controlling the active low clear input. It is not hardwired in this case. S1 is hardwired to +1. So we can say that is 1 and that is 0. Hardwired. So we are not changing modes of the register here. We have it as a shift left register, as a hardwired shift left register. However, we are using the clear input to do a clear operation to start things off, to kick things off. Our feedback is from QA through a NOT gate back into the left input. And we are not using a parallel load, so we don't need anything over there. DCBA are left open. We are not doing a shift right, so RIN is just left open here. We are not connecting those inputs. So let us try to use this reset underscore L input to initialize the counter. So let us suppose that I do something like this. I make it low, and then after some time I go high on the reset. So what are my initial outputs going to be? When I do the reset underscore L, like during that time, 0, 0, 0, right? So 0 here, 0 here, 0 here, 0 here, right? Okay, so I've this was asynchronous clear. So that means that the moment I do reset underscore L as low, my outputs went 0, 0, 0, 0. Beautiful. What happens next? Next, I would need to bring it to 1 so that I don't clear it, right? So when I don't clear it and clock through, what is going to happen? So you see, let me write these 4 over here instead. If that guy is a 0, that guy is a 1 here. And that one is being fed back. So after the next positive edge, you get 1, 0, 0, 0. Perfect. That one comes in, that 0 goes down, that 0 goes down, that 0 goes down. All right, what happens after the next positive edge? 1, 1, 0, 0. Yes, because this one comes down here, that 0 goes here, that 0 goes here, and another new 1 comes back in. what is going to happen next? What's your next count? 1110. Perfect. And I suppose we can just do this again. All right, what's next? 1111. Perfect. All right, the moment we get this, you see what happens? This guy is going to make this guy go to a 0, right? So now 0 is going to be fed back now. So 0111, yes. All right, what's next? 0011. All right, what's next? 3 zeros and a 1. What's next? That's your complete cycle, right? And everything else was in the middle here. You guys see that? All right, so let's now do a decimal representation of this. For 0000, you got a 0. And then 1. And then 0011, that's 3. 0111, that is 7. After that, 15. After that, what do you have after that? 14. Then 12. 8. 0. Yes, you got it. So you see, instead of counting 4 things, now we are counting 1, 2, 3, 4, 5, 6, 7, 8 things, right? And you know what? While we were doing the analysis of this, I hope you guys saw that because of this NOT gate, we will never have a situation where we will end up in a cycle of all zeros, right? There is a way inbuilt that it'll automatically come out of it. You might have a few incorrect states, but there is a way for it to auto recover. You guys see that? All of this information, LIN just inputs a 1 to QD when QA is 0. When QA is 0, it inputs a 1 into QD. Yes. I wouldn't say it inputs it 1. I would say QD plus equals LIN, right? It has to wait for the next, it has to wait for the next positive edge of the clock for that to happen. A NOT gate also amplifies the logic signal, right? It doesn't amplify it, it regenerates it, right? But in this case, there is no need to worry about the level of the signal because it is right from the output of the chip going back into the NOT gate. So it's not too much of a concern here because there are not too many elements sharing that pin. All of this we can also look at in terms of a timing diagram for the Johnson counter. At the top we have the clock input, free running clock. After that we have the reset input, which is initially set to low. When we set it to low, we start off at 0, 0, 0, 0. After that, we make it into a high signal, which means that we have it as a shift left register. And then we essentially do the 1, 0, 0, 0 and so on, giving us 8 different states. And we also talked about what those are in decimal. 0, 1, 3, 7, 15, 14, 12, 8, and then back to 0. And then that cycle keeps continuing. All right, questions about the Johnson counter here? All right, so what I'll do is I'm going to stop the recording. Oh, hold on. Why do we flip the way we read midway. Uh, uh, can you clarify your question a little bit more, bit? And I didn't. The counting. Why do we flip the way we read? Where did I flip? Are you talking about this? Oh, so you see this guy, when it was 0, the output over here of the NOT gate was 1, and we were feeding a 1 as the left input, so a 1 came in over here. But the moment this last bit, like QA, became 1, this guy became a 0, and we were feeding a 0 back over here. Do you see that now? All right. So why are we doing that? We are only doing that just so that it never goes into this all zeros cycle, and also to increase the number of counting states from 4 to 8. All right, let's stop recording here.